Okay, so let's look at this particular topic, which is sizing of gates in a network. So what we've been doing so far is looking at basically gates in isolation, looking at one single gate and talking about how should we size it. And you know, with an inverter, we came up with that perhaps what we should do is choose the minimum size for the NMOS and then match the PMOS so that its drive capability is similar, right? And we said we'll call that as the 1x inverter, and we also know that we can make a 2x and 3x and 4x and 5x and so on and so forth. So what I want to raise now is, so that was without looking at the context. We are saying that we can make an inverter which is of strength 1x and 2x and all that. But in a particular situation, what size of an inverter should I choose? What size of a gate should I choose? All right, so as an example, let's look at this particular situation here. So we have 3 inverters connected in series, and there is a reasonably heavy load, a capacitive load on this particular inverter, which is 200 femtofarad. Why am I saying it is reasonably heavy? So for the technology that we are talking about, a inverter like this, if I look at this inverter here, and its load is another inverter of the same size, and if we look at the capacitive load here, it would typically come out to be, for 0.5 micron technology, it will come out to be around 20 femtofarad. So the load of this particular inverter, capacitive load, is only 20 femtofarad. And what we have is the third inverter that you see here has been loaded with 200 femtofarad. So 10 times higher capacitive load, right? And what we have done is, you know, we picked 1x inverter, 3 of them. All sizes are 1x, 4 lambda, 4 lambda, 4 lambda here. And we just want to see what happens, what are the delay values, right? So I can, based on now the sizes and everything, I can we can also calculate, but these are results from simulation, which shows you the, so what we are doing is we are driving it with an abrupt input, okay, from 0 to 1. We are driving it with an abrupt input. So the green one shows the output of the first inverter, the green one. So 0 to 1, so output is falling from 1 to 0. The blue one is the output of the second one, which is here. And the red one is the output of the third inverter here, which is falling over here, right? So that's. And now I can calculate the delay of each inverter. Delay of each inverter means 50% of the output to 50% of the input, then 50% of this output measured from 50% of this input, and we can calculate all the delays. The delay comes out to be, for the first one, 81 picosecond, for the second one, 126 picosecond, for the third one, 734 picosecond. Overall delay from input to output is, you add them up, 941 picosecond. Now, do we realize why the delays are in this particular manner? Why is the, this is sort of obvious. Why is the delay so high? Because the drive capability of this inverter is the same size, while the capacitive load is very high, 200 femtofarad. We'll not go into the exact value, but we expect it to be much higher here. You know, as I've been saying, the capacitive load here, 200 femtofarad, is 10 times higher than the capacitive load here, and then you can see here, 81 picosecond and 734, you're seeing roughly 10 times higher delay here. So this is the situation. Why is the delay of this particular inverter higher than this? The second inverter, why is the delay higher than this? Because it's being driven by a signal which has a rise time and fall time, as compared to an abrupt signal here. So 81, 126, 734, right? So overall delay from here to here is very large, 941 picosecond. So now the issue is, suppose we put the constraint that I'm going to use only 3 inverters, so number of inverters is fixed. I am also putting the constraint that the first inverter size I don't want to touch. 4 lambda by 8 lambda here, because this will be driven by some other block. I don't want to affect that previous block. If I change the size here, note if I change the size here, then the capacitive load that this particular inverter will caused on the previous stage will increase, and I don't want to touch that, okay? So the size is fixed here, and I'm free to alter the size here and free to alter the size here, and we would like to minimize the delay, right? Okay, so that's the task here. So this is our default solution, right? So in the next case, note that what we did was, well, this inverter has a high capacitive load of 200 femtofarad, so let's increase the size of this one, size of this particular inverter. As I increase the size of this particular inverter, the currents that are available for charging and discharging, or the drive strength, increases. So rather arbitrarily, one has taken from this inverter and increased the size to 5 times. So this is a 5x inverter. 20 lambda by 2 lambda, you can see here 5 times the size here and 5 times the size here to balance, to maintain a symmetry, right? So this inverter is 5x. What is likely to happen? Can you predict what would happen? The delay values are here. Third stage, decrease. And by how much will it decrease? A rough idea? By how much would you expect it to increase? 5 times? Why? The load, capacitive load, will it remain? Now note that delay, the capacitive load at this particular stage is 200 femtofarad is external, plus it will come from the transistors also. Okay? But, okay, so let's see. If I simulate this is what I get. 306, 242, 81. It didn't fall by a factor of 5. It fell only by, about a factor of 2 or so, a little bit larger than 2. All right. And this one increased. Do we realize why this one is increased? Because the size is increased, so the load is increased, so this 242 here, right? Why has this increased? I mean, why didn't this increase by that much, by a factor of 5? Why? Because note that the delay of this particular gate depends also on the rise time and the fall time of the input. So when you increase the capacitive load on this one, it's no longer 126 picosecond, it became 242 picosecond. And the rise time and the fall time have increased, and that causes this particular one to affect also. So it doesn't decrease by 5. So what we end up getting is 81 plus 242 plus 306, 629 picosecond. Right? Now this is something that is important, and important to note that when we intervene, so we said this particular inverter is loaded with a high capacitance. So when we intervene by making its size larger, in order to reduce its delay, something interesting happens that, well, this affects the previous stage. This affects the previous stage because as you try to improve this particular inverter, it causes a degradation effect on the previous particular inverter here. And that is true in engineering in general. Whenever there is a problem and you intervene to solve that particular problem, invariably you create a side effect. Any medicine that you take to cure a particular something has a side effect. Right? So that's in general, if we intervene in order to improve this particular drive strength so that it can drive this particular inverter, it creates the side effect of a higher capacitive loading of the previous stage here. And therefore, what it's suggesting is that you have to, if you want to minimize the delay, you can't just look at this particular inverter in isolation. Because as you increase this size and you reduce delay, it does something to the previous stage. And so you have to look at the whole system. Now this is probably suggesting to you is that, well, as I increase the size here and reduce the delay to some extent, well, it caused a capacitive loading of this one. So maybe what I should do is increase the size of this one because its capacitive loading is increasing. So I increase the size of this one in order to reduce its delay. All right, so let's do that. So we are at this stage here. We had increased it by a factor of 5. We are here. And in the next case, we increase the size of the second one. Now, so far it's just arbitrary. How much size to increase, I don't know. right? So I increased the size from 8 lambda to 16 lambda here. We double the size of this one. Now, what will be the change compared to this? Can you predict which one will increase, which one will decrease? Second one obviously will decrease because its size has increased here and the capacitive load has remained the same, and the second one will decrease, but then this will cause a increased capacitive loading of the first stage, so its delay will increase. Anything else? Third will decrease, right? Because this will become faster and will cause this to become faster, right? So look at the delays. This increased to 107 picosecond. This decreased to 178. Well, it didn't decrease again that much because its input became slower. Input became slower, so 107, and this 178, 256, and overall delay is 541 picosecond. Now, is this factor of 2 optimum? Should I increase it? Should I increase it from here to here by a factor of 2? Should I increase it by a factor of 3? Will that be better? All right, so this is our default solution. Let me increase it by a factor of 3. Earlier it was 8, so we made it 24, and this was 4, this we made it 12, right? So the first inverter is fixed. Last one, we are still keeping it at 5. Now we made it a factor of 3 here. Well, this is what happens to the delay. 240, 162, 133, well, 535. Is that the best? Should I make it a factor of 4? Should I make it a factor of 4? Or, so this is our default solution. If I make it a factor of 4 here, 32 and 4, 16, what happens? 232, 158, 159, overall delay, 549. It increased. It made it worse. What is it suggesting? It's suggesting that if I fix this also, maybe there's an optimum size of this one. Too low was bad. Keeping it 1x was bad. Maybe keeping it 4x is also not optimum. Right? Why is this question of optimum arising? Because as you increase the size of a particular inverter, why is this question of optimum arising? As you increase the size of this particular inverter, its delay increases, but it causes the delay of the previous stage to increase. And that's why there is a balancing act. Some delay is decreasing, and some delay is increasing. And you would tend to intervene till you find that the increase here or the decrease here is balanced by an increase here. After that, it doesn't make that much sense here. All right, so what have we found? We took this initial design with 941 picosecond. We intervened here, increased the size, came to 629 picosecond. But then this caused a loading here, so we realized that we need to increase the size here. So as we increase, it goes to 541 picosecond. Maybe 2 lambda by, increase it by a factor of 2 is not enough. So we increase it by a factor of 3. This brought it to 535. And then we increased it further, made it worse, 549. So is that the optimum design? Well, to begin with, this choice was arbitrary, right? I increased it by a factor of 5. The choice was arbitrary. Why increase it by a factor of 5? Suppose I increase it by a factor of 4. So compare these two. Factor of 4. This is 629 and this is 617. So if I start from here, increasing the size of this by a factor of 5 is not really optimum, because that only causes delay to reduce to 629, and increasing it by a factor of 4 causes it to decrease to 670. So what you are saying is, yes, increasing sizes helps. This is probably an optimum size. How do I decide? How do I decide? So note that the choices here are, should I increase it by a factor of 5 here, or should I increase it by a factor of 4 here? Once you choose this, once you decide on the last stage, then it comes to the second stage here. Should you choose a factor of 3 here, or should you choose a factor of 4 here? So there are choices at every point that you have to do. And you realize that I can't be doing it empirically by trial and error. Let's try 5 here and then simulate. Let's try 4 here, let's simulate. This is only 3 inverters, right? If I have a chain of 10 inverters or 11 inverters, I can't keep on doing, arbitrarily increasing the size here and decreasing the size here and all that. That number of iterations that it would require would be huge. So this trial and error method, although we understand what the effect of increasing an inverter size has, qualitatively we understand what it does, but it would take too long a time to arrive at an optimal solution. So what we need is a more precise methodology here. All right. So this is what we discuss. How do we do this? So consider the following. Again, it's same problem, except that we now generalize it and we say that we have n inverters in a chain. 1, 2, 3, 4, n inverters in a chain, and there is some load capacitance CL. And note that the load capacitance CL that you see here, I can also model it by saying that instead of CL, I have an inverter of size WN plus 1. Right? Because when you take an inverter and you look at it from the input side, what do you see? You see a capacitance, a CMOS inverter. So you see a capacitance. So CL that you see here, you can also say is as if there's another inverter connected here whose size is some WN plus 1. Okay? Without loss of generality here. The first inverter we are saying is size we are keeping fixed. We don't want to alter it because that would cause impact on the previous stage which is driving it. So this is 1x. And now our task is to determine the optimum size of inverter n and n minus 1 right up to inverter number 2. What should be the optimum size here? All right, so that's the problem that we have. Okay, so let's go back to our delay model here. Tau PHL or tau PLH are the same. So our delay was 0.5 CT, net capacitance, delay of any inverter, CT, VDD by pull down. Pull down current or pull up current is the same. We are talking about a balanced inverter with pull up strength and pull down strength, which is the same here. So if I look at this expression, I can break capacitive load of any inverter into 2 parts here. One is the intrinsic load of that particular inverter, the load coming from the inverter itself, and the other one is the load coming from the next stage here, whatever is connected to it. Okay, so we can break this into 2 parts here. And the first part is what we have been calling as the intrinsic delay of an inverter. And what we have been saying is, to the first order approximation, these are, any analytical calculation that I do would be based on assumptions. So what we are saying is that this part is sort of a constant A, which is the intrinsic delay of an inverter. That is independent of the size. Because what would happen is, as I increase the size of an inverter, the capacitance would increase and the current would also increase, and the two would, to the first order approximation, cancel each other. Okay, so this first part we are calling it as a constant A, intrinsic delay of that particular inverter. Okay, next part, 0.5 CL VDD by I pull down. All right, so 0.5 CL VDD. Now I pull down, if you recall, it depends on the current of the, let's say, the NMOS. When I'm talking about W and all that, we are talking about the size of the NMOS. Because the size of the PMOS would be twice as large as the size of the NMOS in all cases here, okay? So the current, note that current would be proportional to W, KPN, and plus other things that are there. VGA, VDD minus VT and all those other things that are there. We're not bothered with all of that here, okay? So this is here. All right, so whatever that, the current would be proportional to the width of the transistor, the KPN, and plus other things that are there. Okay, so let's not bother about it. Let's just put it as F. I can write this as A plus this whole factor that you see here. Because CL, as I said, the load, if I look at the load one, I can model it as another inverter of size W, some size W. Okay? And so I can write this as the inverter delay is A plus B, the whole thing B, Wi plus 1 by Wi. Right? So this is, suppose I'm talking about the ith inverter. So ith inverters, load is what? Load is the input capacitance of that particular inverter. So that load CL would be proportional to Wi plus 1. The input capacitance of that particular one would be Wi plus 1. So what I can say is, in general, if I look at any inverters, its delay can be written as an intrinsic delay, A, plus some constant B. Let's not bother, we can determine this B also, multiplied by Wi plus 1 by Wi. Wi plus 1 is the load capacitor of that particular inverter, is proportional to, is the I plus 1th inverter, and therefore is proportional to its width here. And the current here, this refers to the current is proportional to width of that particular inverter. So tau I is here, right? And so, and as I said, we have a balanced inverter, so high to low and low to high delay is all the same, okay? All right, so the total delay from here to here will then become, you add up tau 1 plus tau 2 plus tau n will become n times A plus B. The delay of the first inverter would be proportional to W2 by W1, and like that you end up with the load capacitor we are saying is like Wn plus 1. So this will be Wn plus 1 by Wn. All right, so that's the total delay of my chain of inverters here. Okay, under the assumption that each one can be written as made up of a constant term A plus B Wi plus 1 by Wi. So now this is what the total delay is, and we want to find out the optimum size. W1 is fixed. We want to find out optimum sizes W2, W3 and up to Wn here. So how do we find optimum size? Well, we take the partial derivative with respect to that. Okay, so we take this expression and we take, if you want to find out the optimum size of the inverter ith inverter, you take del tau by del Wi equal to 0, and that basically tells you if, and similarly you can find out the optimum size of any one by taking its derivative with respect to that particular width equated to 0. And what you find is, when you take the derivative, that W2 by W1 equal to all of these, this relation comes out and is equal to F. That's the relation that you end up with, that you find that W. So when you take it, let's say with respect to W2, so what you will find is W2 by W1 equal to W3 by W2. And similarly you'll find for any particular inverter. So this is the relation that you end up with, that the size of the second inverter divided by the size of the first inverter must be the same as the size of the third inverter divided by the size of the second inverter, and like that all of them. And let's suppose this factor is F, whatever is this ratio. W2 by W1 is F here. So then this is here. So it tells us, interestingly, that if I have a chain of inverters, then for minimum delay, it turns out that the delay of each inverter should be the same. Because delay of each inverter is what? A plus B, Wi plus 1 by Wi. What is this relationship telling us? The Wi plus 1 by Wi is a constant F. And so for every inverter, the delay is the same. So when you have a chain of inverters, how do you obtain a minimum delay? Well, the target is make the delay of each inverter the same. That's what this particular relationship is saying. Each inverter's delay is the same. So you distribute the burden. The burden of driving that large capacitive load at the end, you distribute the burden over all of them equally. And each one shares that particular burden. Okay? And the minimum delay that you end up with is N, obviously N times A plus B times F here. So how do we find this F? Well, so we said W2 by W1 is F, W3 by W2 is F, all of them are equal to F here. Multiply them together. Multiply W2 by W1 into W3 by W2 and all that, you multiply them together and you get Wn plus 1 by W1, the width of 1, equal to F to the power N. Now, what is Wn plus 1? The load capacitor. We said the load capacitor can be modeled as an inverter of size Wn plus 1. So Wn plus 1 is known, and W1 is also known, width of the first inverter. We said is fixed. For example, for us is 4 lambda. So it's fixed here. So F to the power N, and therefore we know the value of F here. So what is that ratio? W2 by W1 and W3 by W2. What ratio should we maintain? We get the value here through this particular relationship. Okay. So F is nothing but Actually, because as I said, Wn plus 1 is proportional to CL, and W1 is proportional to the input capacitance of the first stage here. You can talk about, each capacitor is proportional, so the input capacitance of this one is proportional to W1. So what we can also write is F is equal to CL by input capacitance of the first inverter to the power 1 by N. Because we are modeling a capacitor as if when you look at it from the input side, what is this value here? So CL by C in 1, 1 over N, so that gives us the value of F, and tau min then becomes N A plus B, whatever, CL by C in 1 to the power N. So we end up with a methodology for sizing the inverters by basically maintaining the ratios of of one inverter with respect to the preceding inverter the same ratio. And how do we find that ratio? That ratio is nothing but the overall load capacitance divided by the input capacitance of the first stage into 1 by N. Well, how well does this work? Let's see. So if I go back to my initial problem was those 3 inverters that were there, and the load was 200 femtofarad. And so if I apply this technique to our inverter, what would happen? So CL is 200 femtofarad. The input capacitance of my load of this particular inverter is 7.2 femtofarad. Of size 1 is 7.2 femtofarad. We have shown this calculation is made up of CGS of this and CGD of this, CGS of this and CGD of this. And if you add this up, it comes out to be 7.2 femtofarad. So CL is 200 femtofarad. C in 1 is 7.2 femtofarad. Number of stages we have fixed to 3. And so we calculate F comes out to be 3. 200 by 7 and 1 by 3, if you do, it comes out to be, if my calculations are correct, it comes out to be 3. So what it says is the following. This size is fixed, so I should make this 24 lambda by 12 lambda, size 3, 3 4s are 12. And what should I do to this one? 72 lambda by 36 lambda, 3 times the size of this one. That's what this particular method is saying. Make this the size here. Now, okay, so I took this one, I simulated it, and these are the delay values that I get. 133, 208, 200 picosecond, overall delay, 541 picosecond. Now, remember what this method is trying to do? Is trying to equalize the delay of each particular inverter by taking the ratio of this to this and the ratio of this to this to be the same, is trying to equalize the delay. So yes, 200 picosecond and 208 picosecond, reasonably close. This didn't come out to be the same. And we can see why it didn't come out to be the same. Because note that the method is failing to some extent. Why? Because it's assuming that each inverter is of the same kind. While these inverters, note this inverter is driven by a rising and a falling input with certain rise time and fall time. This one is not being driven by that. This is being driven by an abrupt input. And therefore, the method sort of fails. And also note that the capacitances and all that are not fixed. C input is not 7.2. As the inverter is going from cutoff to linear to saturation, all these things are changing. All right? And the currents are also changing. So this is a approximate technique which is telling us, and maybe, so I've not done that, maybe we take a chain of 10 inverters. If we take a chain of 10 inverters and then if we size it, perhaps the results that come out are closer to, because one inverter will not make so much difference there. If I have a chain of 10 inverters, 9 of them are in the same situation and 1 of them being driven by an abrupt, perhaps it will not make so much difference here. Anyway, so this is the method here, so which is telling us, is that perhaps the strategy for sizing the inverters is to share the burden of delay on each one of them equally, and to do that, then you size them such that the ratio of the size of one inverter to the next remains the same as you go from one end to the other end. All right, now this is for the inverter. Now what we want to take this particular method that we just talked about for the inverter and generalize it to a arbitrary gate. Any gates that we have. If we can have this an inverter, this inverter input may be going to a NAND gate, this may be going to an XOR gate, and more complicated things. And then we want to know how do we size it. Now, before we go to that, remember, the other issue is, for example, we have 3 inverters, right? Nobody is stopping us. I mean, it doesn't change the functionality if I add 2 more inverters to it. If I add 2 more inverters to it, as far as the function is concerned, from input to output is still causing an inversion. So I can have 5 inverters in a chain without changing anything. I can put 7 inverters in a chain. So the issue is also, what is an optimum number? If you have to drive a load, let's say capacitive load, 3 is given, let's say, but 3 may not be optimum. I can add 2 more, and then it becomes 5, and still the same functionality. Maybe I get n becomes lower. Then CL by C in 1, so you get 1 by 5, right? So F becomes lower, but then this n becomes larger, right? So there may be an optimum number of n. You could take 1 also. But if you take 1, as I said, you are not going to change its size. That first inverter, we are not going to change its size because it will cause a burden on the previous one. We don't want that. Our starting point is 1. So you can take 1 and you connect 200 femtofarad directly to this. And so you calculate what is the delay. Then the next possibility is you take 3, and then you take 5, and then you take 7. Now you see 2 things are there. F is decreasing as you increase n, but then there's a multiplying factor n here also. So you're also saying that there would be a optimum n. There would be an optimum n for which the delay would be minimum. Okay, so we'll come back to that later on. Let's take this particular method that we are talking about and generalize it to arbitrary gates. So the method, when you generalize it by arbitrary gates, the method was described by these 3 authors, and they gave a name of this particular method is called logical effort. Okay, the name is logical effort. And so the central thing is, first of all, that modeling the delay of a gate as made up of 2 elements here. Remember, the inverter delay, we also modeled it as 2 parts, an intrinsic delay and an extrinsic delay. So here also they take the delay of any gate and they normalize it by a delay of an inverter. First of all, they talk about normalized delay. Now, delay of which inverter? Delay of size 1, 1x inverter. So whatever is the delay of that particular gate, normalize it by a delay of an inverter of size 1, which is for us, let's say 4 lambda by 2 lambda and 8 lambda by 2 lambda here. So tau by tau naught, they say, is made up of 2 parts. And the intrinsic part, they also call it as the parasitic or the intrinsic delay of a gate. And multiplied, and this is the extrinsic part. And the extrinsic part, they write it as 2, product of 2 things. One is what they call as the logical effort, and the other one they call as the electrical effort. Logical effort, you will see, is the characteristics of a gate. For an inverter, you'll see G equal to 1. For some other gate, NAND gate, NOR gate, and all that, G will come out to be other values. And the logical effort, the electrical effort would depend on the loading of that particular gate here. All right, so let's see what is the basis of this. So this is the model for the normalized delay of a gate, P plus G into H. G is logical effort, H is the electrical effort here. So remember, this tau that we have been talking about is 0.5 VDD net capacitance divided by current I. All right, and we have said that capacitance can be broken up into the intrinsic capacitance and the load capacitance here. Intrinsic capacitance, according to their terminology, they're also calling it parasitic capacitance. All right, so let's keep CP for example. So 0.5 VDD CP by I, 0.5 VDD CL by I. So far, things are fine. Tau, this is the intrinsic delay. 0.5 VDD CP by I is intrinsic tau P here. And this tau P normalized by the delay of an inverter. I can also write down the delay of a inverter. I normalize it, and we'll call this, the first part is as the P part here. the first part. So first part is straightforward. There's an intrinsic delay. If you divide it by tau naught, you divide it by that and you get the intrinsic delay of a gate normalized by the intrinsic delay of an inverter. So that's okay. Let's come to the second part. G into H. What is this G into H here? So 0.5 VDD CL by I. Now this one, 0.5 VDD CL by I, is being written as CL by C in into 0.5 VDD C in by I. Now what is C in? Input capacitance of that particular gate. Okay? CL by C in is the input. So CL is what? The load capacitance of that gate. And C in is what? The input capacitance of the gate. Alright? So I'm allowed to do that, to multiply and divide by this factor here. CL by C in and C in by I. Now this factor CL by C in is what they're calling as the H here. Electrical factor. Electrical effort. And this part, this whole thing that you see here, they're calling it G. Now alright, so this part is clear. CL by C in is the ratio of, what is it? Is the ratio of the load capacitance to the input capacitance of that particular gate. Okay, CL by C in. So that's our H here. It's a ratio, dimensionless ratio here, so that's the H part here. Let's look at this particular factor in a little bit more detail here. So suppose the gate that we are talking about, gate under consideration is of size X or whatever. Then note that its input capacitance will go as C, whatever is the input capacitance of size 1 multiplied by the size factor, and the current will be equal to I naught multiplied by the size factor. What is this I naught and Ci0? A gate of size 1x. Gate of size 1x, not inverter of size 1x. Gate of size 1x. Okay, so the gate that I'm talking about may be of some arbitrary size, maybe 2x, 4x, 6x or whatever. Okay, so we can say C in is Ci0 into this factor here, and I is also into this particular factor here. Alright, fine. So I can write this down now into this particular form. This part here. Tau 0, CL by C in is here. And so what we do is, note that C in that you see here, I write it as C in 0 multiplied by this factor here, and I write it as I0 multiplied by this factor. So these two factors cancel out. So I get Ci0 by I0. Ci0 by I0. And then Ci0 of that particular gate and I0 of that particular gate. But which gate? Size 1x. Size 1x. And then we normalize it by the Ci0 of the inverter and I0 of the inverter. And so what we end up is that we can write this whole term as tau 0 CL by Cn into Ci0 of that gate by Ci0 of the inverter. Note that what is the tau naught? 0.5 VDD, Ci0 of inverter and I0. I0 is of the inverter of size 1x. So we end up writing in this particular form here. Now remember, this is tau by tau naught. So you take tau naught to the other side here, and CL by Cin becomes, as I've said, the electrical effort, and Ci0 of that gate by Ci0 of the inverter becomes the logical effort, G. Now what are we talking about? Ci0 of a gate, which means what? A gate of size 1x. And Ci0 of inverter means an inverter of size 1x. And that ratio is what we are calling it as the logical effort, G. And so this is a constant, because we are talking about 1x gate and we are talking about 1x inverter, and we are talking about the ratio of the two capacitances. So this is a constant here. For a gate, it's a constant. H will depend on what load I attach here, CL by Cn here. Alright? So this is what one is talking about. H is CL by Cn, electrical effort, and logical effort is Ci0 gate by Ci0 inverter is 1x drive strength. So there are a lot of terminologies. It will take some time to become familiar. So this is the net model then. So what we are saying is the normalized delay of a gate is an intrinsic delay, P, plus G, logical effort, Ci0 by Ci inverter, and the electrical effort, CL by C. Okay, let's apply that here. So let's keep that. So first of all, what is this logical effort? Keep that in mind. Logical effort I have to calculate. Each gate will have a logical effort. Each gate. And how do we calculate? Input capacitance of that gate divided by input capacitance of the inverter. All of the same size 1x. So obviously this is our size 1x inverter. Size 1x inverter. What is this input capacitance? Well, input capacitance would be we are doing a simple calculation. Input capacitance of this particular inverter would be proportional to the width here. Let's say this is 2 and the width here, let's say this is 4. So the input capacitance of this particular inverter, you can also, we can call it a 4. We can call it 4 lambda and we can call it 8 lambda. So you can also call, it doesn't really matter. You can put here 4 plus 8, so you'll get 12. And some multiplying factor s, doesn't matter, because we'll be taking ratios. We'll be taking ratios. So anyway, the logical effort of a inverter, so Ci0 of an inverter divided by Ci0 of inverter obviously is 1. Okay, so that doesn't matter here. Let's look at a NOR gate. NOR gate, this is a NOR gate. Now NOR gate of size 1x. NOR gate of size 1x, note that we have put 8 and 8 here. Why? Because our normal inverter was 4. So we put 8 here and 8 here, and we put 8 here and 8 here. So the input capacitance of this one is 8 plus 8. So 16 units here. And input capacitance of a 1x inverter was 8 plus 4. So ignore this. We have put 2 and 4. So put here 4 plus 8. So put it here 12. Okay. So input capacitance of an inverter is 12. So the logical effort of a NOR gate is 16 divided by 12 is 4 by 3. So that's how you calculate G value. For every gate you can calculate G value. Look at this for a NOR gate here. There's a NAND gate here, sorry. And this is a NOR gate here. So this is 4 and 4. And you'll size it as 16 and 16 to maintain the same drive strength as 1x inverter. So input capacitance is 4 plus 16, 20. And so G is 20 by 12, 5 by 3. Right? So for every gate that is given to you, you should be in a position to calculate what is this logical effort, G. All that you have to do is, for that gate, size the PMOS network of strength 1x and size the NMOS of strength 1x. And look at the capacitance. Look at the capacitance and normalize it by the capacitance of an inverter, and you get 5 by 3 or 2 by 3 or whatever. Right? Now, is this example clear? How do we calculate the delay under this situation? Can we apply this model? The delay, normalized delay, tau equal to P plus G into H. So if I want to calculate the delay of this particular inverter number 1, its normalized delay would be tau 1 would be its parasitic delay P1 plus its logical effort multiplied by electrical effort H1. What is the logical effort of an inverter? Basically 1. What is the parasitic delay of an inverter? Is also 1, because it's all normalized by the delay of an inverter. So it's 1. 1 plus 1. Electrical effort is CL by CN. Electrical effort is CL by CN. What is CL? These are 4 identical inverters. So CL will be equal to 4 times CN, whatever is the input capacitance of this. So 4 here. So 4 plus 1, 5. So the delay of my inverter number 1 would be 5 units. What are the units? The delay of a 1x inverter. Everything is normalized by 1x inverter. Right? So we calculate the delay of this particular one. It will come out to be 5 units here. Of course, it's based on some approximations. These are approximate values. This is just to, when you're designing, this is just to get started the design, and then you can simulate and tweak and all that you can do here. Do these make sense? Delay of the first inverter, parasitic delay 1, logical effort 1, electrical effort is 64. Now, all these values that are given, 64, this is in terms of 64 times the input capacitance of an inverter. Okay? So this is 64 times the input capacitance of an inverter. So 1 plus 1 into 64, 65. Suppose I put 1 and 8 size here. See if it makes sense. If you apply the same formula, P plus GH. So the first inverter, 1 plus 8. What is the load of this? 8, size 8. And what is the input here? 1. So electrical effort is 8. And the electrical effort here is also 64 by 8. 1 plus 8. So the 18. 3 of them if you take, calculate in this manner, 15. 4 of them if you take, calculate in this manner, 15.3. So any chain of inverters, if I give you with some sizes, you should be able to use this particular expression and calculate what the overall delay is going to be. All that you have to do is P plus G into H. For an inverter, G is 1, P is 1, and electrical effort is nothing but the ratio of the load capacitance divided by input capacitance. All right, this becomes now the place where we really apply the method here. We have a 3 chain of inverters here. 3 chain of gates here. CL is given to us, and this is also given to us. The first gate, the size is given to us. If the size is given to us, note that what is given also is the input capacitance of the gate. Then fix. So first gate size is known, CL is known. All I have to do is find out the size of this NOR gate, inverter, and XOR gate. What is my starting point? Starting point is to find out, the delay, overall delay is going to be P1 plus G1 into H1, first one, P2 plus G2 into H2, like that, the overall delay is going to be. Starting point is going to be, okay, fine. So G1, C2 by Cin, C3 by C2, Cl by Cin. This is what H1s are. Now to apply this, I need to know what is the logical effort, G1 and G2 and Gn and all those things I have to know. Okay? All right. Okay. So suppose I know this P1 plus G1, I know P2, G2, I know Pn and Gn and all these things that I know. These are the characteristics of a gate. Now the issue is, what size should I choose? What size should I choose for this one, and size for this one, and size for this one? Now size, note that as I change the size of this particular one, what will change is C2. As I increase the size of my gate, C2 would increase. As I increase the size of my inverter, C3 will increase. So size determination is same as capacitance determination. What is the input capacitance looking from here? What is the input capacitance looking from here? And same. Because our equation is written in terms of C2, C3, and in terms of this. So once you determine the capacitances, you determine the size. There's a one-to-one relationship between them. All right, so this is the equation that we have. It's the same method. If you want to find out the optimum size of C2, you take the derivative of tau with respect to C2. If you want to find out the optimum size of C3, you take the derivative with respect to C3 here. And what do you end up with? Del tau by del Ci equal to 0. And so effectively what you end up with is Gi minus 1 by Ci over Ci minus 1 is equal to Gi Ci plus 1 by Ci equal to the same throughout that you end up getting. Note that if you take with respect to C2, you will get G1 by Cn, plus you will get G2, and you will get C2 square, and then you can rearrange, you will get this here. So remember, our earlier condition was Wi by Wi minus 1 equal to Wi plus 1 by Wi. It's similar, except that now it's more generalized. It's more generalized. Ci and Ci minus 1 are proportional to the size of the transistors here. So we get this here. Now note that what this is telling us is the ratio of this is nothing but the electrical effort. So what this is telling us is that for optimum size, each gate should have the same effort here. The logical effort multiplied by the electrical effort. G1 into H1 must be equal to G2 into H2 equal to G whatever. Has to be the same. So the method that we talked about in inverter is now generalized to an arbitrary gate with G1 into H1 equal to G2 into H2 equal to G3 into H3 and so on and so forth. Okay, and G1 into H1 and all that, so you can multiply all of them together, multiply all these terms together, and you can write F is equal to G into H 1 over N. And so G is equal to G1 into G. These are all constants for a gate. H is equal to H1 into H2 into this one, comes out to be CL by Cn, which we know, load capacitor we know, and input capacitance also we know. And therefore we know the value of F here. Okay? So the method of logical effect can now be summarized as Find the path logical effort G1 into G2 into Gn. Find the path electrical effort CL by Cn. The path effort, total path effort is made up of logical effort and electrical effort. F is equal to G into H. For minimum delay, each gate should have the same effort. F is equal to G into H 1 by N. And the minimum delay is sigma Pi plus N G into H 1 over N.